Now that we've talked about beams and external forces, let's talk about beams and internal. So in order to see internal forces, we know we need to make a section cut. So let's just start by making an arbitrary section cut and looking inside a beam. We're going to cut between the 200-pound forces and we're going to look to the right. So I'm going to have a tiny piece of beam. It's going to have 100 pounds on it. And internally, when we cut a beam, we have three internal forces. We have a shear force, we have an axial force, and we have a moment. And when we look at these things, shear forces, when we look at these things, we can use our three equations of equilibrium to solve. Now, in this cut, we can cut a bunch of times to the right of it, and we're going to find that really the shear and the axial force change, but the moment is going to be changing with length. Now, let's go ahead. Well, we could go through, and if I had a bunch of students here, I'd give each of them a different cut, and we'd cut this beam up and do a ton of calculations so that we could plot how these internal forces, shear, axial, and moment change over the length of this cantilever beam. Now, since I don't have a bunch of people here to do it for me, and I'm not going to do all the hand calculations by myself, I'm going to do something smart and employ a computer to do the cuts for me. So what we're going to do is we're going to do two section cuts. We're going to keep the one we have, and we're going to make another one between the support and the second 100-pound load. I'm going to call this cut A. This will be cut B. And we're going to write generic equations going from the left-hand side. The distance to cut A I'm going to call L1. And the distance to cut B I'm going to call L sub 2. Now, let's work on section cut A. Now, internally, I'm going to have shear, axial, and moment. And I can use my three equations of equilibrium to get them. So if I sum forces in the x, that has to equal 0, and we'll find that A equals 0. Okay? So A is going to be 0 anywhere between the support and the first point load. If I sum forces in the y, it has to equal 0. 0 is going to equal B minus 100 minus 100. I'm going to know that my shear force is going to be equal to 200 anywhere between the first support and the only support and the point load. If I sum the moments, now The section cut is at a random spot L1. So if I sum the moments at L1, it's going to equal 0. So the 0 will equal, I drew the moment going negative, so I'll say minus m plus 100 times 30 minus L1 plus 100 times 60 minus L1. So in this case, our moment is a function of L1. The axial is not and the shear is not. So 0, so our m will equal 3,000 minus 100 L1 plus 6,000 minus 100 L1. So our moment is going to equal 9,000 minus 100 times L1. And for this case, L1 goes from 0 to 30. Okay? Now, let's clean this up, and we'll do the left-hand side. Or the right-hand side. So now we have the right-hand side. The cut is happening at L2. If we sum forces in the x, they have to equal 0, so we find that A equals 0. If we sum the forces in the y, they have to equal 0. So we say 0 is equal to V minus 100. And now we know that V equals 100 between the 2 point loads. And if we sum the moments around L2, it has to equal 0. So summing the moments around L2 says 0 needs to equal minus m plus 100 times 60 minus L2. In this case, the moment has to equal 6,000 minus 100 times L2. Now, this gives us, well, 6 equations. We have A, V, and M between the support and the first point load. We have A, V, and M between the 2 point loads. The axial force for both of these was 0, so it's very uninteresting, so we're not going to look at it. But we're going to look at our shear force. We have V1, V2, M1, M2. So let's take these equations and do a little computer programming. So to get started with this, we're going to just create one column and we're going to call it length. And it's going to go from 0 to 60. And just to make our life a little clearer, at 30, we have a point load. So I'm going to take this point that's 30, and I'm not going to have 30. I'm going to have 29.999, and then I'm going to have 30.001. Essentially, two numbers that are really close to either side of 30, but not exactly 30. Then I'm going to go and I'm going to do my shear equation for portion 1 and my moment equation for portion 1. My shear equation for portion 1 was 200, and my moment equation for portion 1 is 9,000 minus 100L. It is actually not minus 100L. Minus 100 plus minus 100 is minus 200L. So it is 9,000 minus 200L. So my V equation, I'm just going to say 200 and stick with 200 and copy that all the way out, down. That's great. My M1 equation is going to equal 9,000 minus 200 times our length L. So I'm going to double click, copy that equation down. Then I'm going to go and make V2 and M2. V2, I remember, was 100. M2 is 6,000 minus 100L. Now, we've programmed all those equations, but they don't exist in all the same places. So what we're going to do is create a cell that chooses the proper function. So we're going to call this capital V and capital M, which will give us the shear and moment. So our shear has two choices, and to choose between them, we're going to use an if statement. So we're going to say equals if. And what's going to determine it is the length. So if the length is less than or equal to 30, we're going to use V1. If not, we're going to use V2. So we double click, that copies it down. If we scroll down at 30, Or at 29.99, we have 200. At 30.000, we have 100. So our if statement was working. We're going to use the same thing. So actually, I'm going to pull this over and see if it works. So we're not using v1. We're going to drag this over because we want it to be the length. So if a2 is less than or equal to 30, we're going to use m1, if not m2. That's the right equation. So we're going to click that and copy it down. And we see here that we have two very close values at 29.99 and 30.33, which is very nice. It's kind of what we want. Now what we're going to do is make two graphs. So I'm going to say insert scatter XY chart. I'm going to right click on it and say select data. I'm going to add. We're just going to do two different charts for shear and moment because they won't plot correctly together. Our X value is going to be our length. Control Shift down is what let me jump to the bottom there. The Y value is going to be our shear. I'm going to create delete the chart title because I dislike the chart title. And let's make this, instead of a bunch of dots, let's change the chart type to be XY scatter, but we'll just use line segment. So there we've plotted what happens in the shear. Let's copy this. And length is going to stay the same. We're going to drag it over and we're going to plot moment. Oh. What we have to do here is format our axis because our maximum is not. Oh, wait. Well, our moment diagram should begin and end at 0, but here we have it beginning and ending at not something. So let's go back and figure out what we did wrong. So what we did wrong is not wrong. We failed to recognize that our moment is plus or minus here. So this is generally positive, but we chose our moment to go in the negative direction. So we need to negate everything if we want to get a correct diagram. So let's go back and do that. We can do that simply by going in here, multiplying by -1. This needs by -1. And there we have the proper moment diagram. So Now we have graphs of shear and moment. We can go in and look and see what's happening. So if we look at our first graph, we have two constants. The first constant it stays constant at 200, and right at the middle, oh, not in the middle, but at 30 inches, which is the middle, we see a jump. It goes from 200 down to 100. If we look at what our beam was, we have 100, we have 100, we had 100 here, or 200 here. This will be 0. Our moment acting this way would be 9,000. And if we look at what happens here, looking at the point loads, at point 0, we have a force of 200 acting up. So we can go from 0 to 200. That 200 stays constant until we get to this 100 in the middle, where we go from 200 and it jumps down to 100. That 100 stays constant until we get to the 100 on the end, which force everything back down to 0. Shear and moment diagrams need to begin and end at 0. That is a function of everything being in equilibrium. And that falls into place with the shear diagram we just created. If we look at, we say we start at 0, we have a 200-pound reaction force up, so we go from 0 to 200. There's no other forces on the beam, so as we go from 0 to 200, it stays constant at 200. Then we have 100 pounds, which causes a jump of 100. Then we have no other forces till we get to the end, so it stays constant at 100, and then we have another jump of 100 due to the point load. This diagram behaves this way basically because these 100-pound point loads are impulses. They cause the shear diagram to jump. Now, you'll just have to believe me on this, but if we look, or maybe you don't, if I use the investigator, or we can use what we have over here. If we look at M1, M1 begins at minus 9,000. That minus 9,000 corresponds to the reaction moment of 9,000 right here. So we go from 0 to minus 9,000 because of the supports. We have one line from 0 to 30 and a different shaped line from 30 to 60. So since we're in Excel, our life can be made really easy by doing simple calculation in a cell. So let's figure out what the slope of this first line is and the slope of the second one. So we'll call it S1, which you can't see because of the shear diagram, and S2. S1 is going to be equal to, and we can use any points on the line, it'll be the change in x over the change in y. So if I say that x is the moment, so if I say this minus this divided by this it comes out to tell me that the slope is 200, which is very interesting because the slope of this line being 200 matches to the value of the shear diagram from that segment. Let's do S2. So S2 will work for any L greater than 30. So we're going to say S2 equals this minus this divided by so lo and behold, S2 is equal to 100. 100 is the value of the shear diagram between the 2 point loads. Now, considering this, if we have the slope of one line, well, being a function of something that is a constant, we have a straightforward relationship set up there. What that is telling us is that the change in the moment, or the slope of the moment, so the change in moment over dx, or the length, is equal to the shear, and that since our shear was constant and we had no load, we can say that the change in the shear is equal to the change in the loading function, and we'll call that minus Wx. For the case that we just looked at, there are only point load functions on the beam. And since there are only point load functions, there's only functions at individual points. So anywhere in between them, from here to here, the function is 0. So if we look at the loading function being the derivative of the shear, if we take the derivative of our constant shear, we're left, or the derivative of a constant is 0. So the derivative of the constant shear, in our case, was not a function, but it is 0. Now, this is backwards, us basically knowing what the moment is and what the shear is. Generally, we know what the loads are. So it's more beneficial to understand the integral relationship, knowing that the shear is equal to the integral over the length of Wx, where x is a portion along the length. And we know that the moment integrated over the length, or the moment is the integral of the shear over the length. So this relationship holds and allows us to easily construct shear and moment diagrams. What we did in Excel is numerically construct a shear and moment diagram by we did 65 calculations very quickly to get our shear and moment diagrams. We can do these by understanding the function and doing our integration. screen over, which is never going to line up again, I guess. But we understand that the shear and the moment and the load are all related through integration. Now, generally, what we know is the load. So let's say that we did have a load function and it was constant. If the load is constant and we integrate a constant, our shear will be linear. If our shear is linear, our moment will be parabolic. We're going to use this to quickly and easily construct shear and moment diagrams.